and welcome to IAC 101, a video series created by the Industrial Assessment Center Program, or IAC, funded by the U.S. Department of Energy's Advanced Manufacturing Office under the Energy Efficiency and Renewable Energy branch. I'm Dr. Mike Muller, Professor of Mechanical Engineering at Rutgers, the State University of New Jersey, and since I've been doing this since 1986, they asked me to be the host. In this series, I'll be breaking down the various energy systems you may encounter at a typical manufacturing plant, providing both a general system overview and a more in-depth focus on the energy efficiency opportunities of whatever system we're looking at. The series is geared toward facility personnel who may not have in-depth knowledge of these topics, but as well, maybe there's some tips here that could prove useful to people more familiar with these systems. But first, a little bit about who we are and what we do. Since 1976, the Industrial Assessment Centers have helped small and medium-sized American manufacturers to reduce energy use, reduce waste, and increase their productivity. The 28 IACs located at premier engineering universities around the country send teams of faculty and engineering students into local manufacturing facilities to provide a no-cost assessment of energy and water usage, as well as an analysis of their waste streams and overall productivity. Under the direction of experienced professors, the IAC engineering students analyze the facility's energy, waste, and water systems, including things such as compressed air, motors, pumps, process heating and steam, industrial cooling, among others. The IAC teams then develop a detailed report with several energy saving and other improvement recommendations, estimating related costs and payback periods. These recommendations can be found online in the database with data from over 18,000 assessments over 20 years or so. The Center for Advanced Energy Systems at Rutgers, of which I am the director, serves as field managers for the DOE's program. My team's job is to oversee the technical quality of the assessments being performed by these schools. In this first episode, we'll cover industrial compressed air systems. In fact, it's going to take 2 episodes to cover all of the important parts. Episode 1 looks at the supply side, essentially hardware you find in a compressor room. Episode 2 looks at compressed air distribution and appropriate and sometimes inappropriate end use. Now, we're all familiar with air compressors if you've ever filled up a tire or a sports ball or watched people breaking up concrete on the street, you've come in contact with a compressor. In factories, there are a large variety of needs for compressed air: pneumatic tools, actuators on machines, using air to fluidize powders and liquids, and many more. While difficult to do, one valuable exercise is to consider both the pressure and the flow of air needed throughout all of the end uses in your plant. Then you want to add in another 10% because there's going to be some leaks in the system. And then we have a rule of thumb that says 4 CFM are needed per horsepower, and so then you have yourself a sizing. You can size your air compressor. How does it match the installed capacity of the air compressor you currently have? Now, because compressed air is not billed, people tend to think it's cheap. Not surprisingly, that makes it often poorly used. Truth is, between 5 and 20% of the electricity in a plant goes toward compressed air. Some people say it's a $1.5 billion per year expense just for compressed air. This combination of high cost and questionable attention to performance is the reason we're focusing on it. Often you can improve the performance of a compressed air system by 20 to 50% with some simple and relatively minor fixes. The IAC program deals mostly with factories that are already operating, so they already have compressed air systems in place. For small and medium-sized factories we serve, these compressors can range anywhere from 25 to 600 horsepower, with the average being about 100 horsepower. So let's visit the compressor room and identify the what and why of what is there. And we begin with the compressor itself. Typically there are 3 types: reciprocating, which is very much like an engine; rotary screw, which captures the air between the rotary screws and pinches it to provide higher pressure; or centrifugal compressors, which create a great swirl of air, throwing it outward where its pressure increases. These centrifugal machines are great when you need very high pressure and tend to be on the large size, so we don't see them very often. Now back to recips. They operate just like a car engine. The piston goes up and down, driven by a shaft, and valves open and close to create high-pressure air. There's going to be a certain amount of pulsation of the air because of the oscillating pistons. And to be honest with you, they don't rotate all that fast. You can usually hear them miles off going boom, 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 boom. So you need some surge tanks to level out the flow. When a compressor brings a system up to pressure, it then needs to idle. So it operates part of the time loaded and then the rest of the time unloaded. The energy used when unloaded is a big waste, and therefore compressor selection and how it operates in an unloaded mode is key. The reason I bring that up here is one of the best things about recips, especially for smaller type operations, is that you can operate them in an on-off mode. When you reach the desired pressure, you turn the air compressor off using a storage tank to provide compressed air to your facility. When the air in the tank is used up, you start the compressor back up. Terrific, very efficient for the right application. Now, if you can't do on-off, a lot of times you simply will run unloaded by opening the valves, which reduces the amount of energy that the compressors consume. Perhaps more common than recips are rotary screw compressors. They're not centrifugal machines. Air is captured between two meshing helical screws called rotors, which pinch the gas as it moves through the threads, creating higher pressure. People like them because the air is delivered smoothly and quietly. No pulsation like the recip. But there is a higher waste of energy when you unload it. What are you going to do? You can either bypass with high pressure air and recirculate it around itself, or just operate against dead head. Either one of these cases is a waste of money. The thing to recognize, especially with screws, is you may be drawing anywhere from 50 to 60% of the energy you would have used when the thing is loaded for when it's unloaded. One terrific answer to the loaded-unloaded issue is to use a variable speed drive on the compressor motor. These drives operate at some fraction of the 60 cycle per second that most motors would run at, and therefore they can continuously regulate the output capacity on screws, eliminating all offload energy waste. This is ideal if you've got a compressor that's swinging up and down and having lots of different loads. On the other hand, if you've got something pretty steady, it doesn't make the sense to spend the extra money for the VSD control. What remains is a difficult question to answer is whether it makes sense to retrofit a variable speed drive into a situation which currently has a regular drive. We don't see it very often, but we write it up sometimes, and there are people who are interested in it because they know how good it would work. I'm not sure how much money you save or how long it would take to get your money back from doing that upgrade. Another big issue with screws is sealing. You need to seal the air between the screws so the air doesn't leak out. And you can do it in a couple of ways. The most common way is to fill the bottom sump with oil. Then as the screw rotates, it picks up and creates an oil film, providing the sealing. Works fine, but the problem is that the oil can come out into the air. In some cases you don't mind, but in other cases having oil in your compressed air is a big problem. You can buy an oil-free screw where the tolerances in terms of manufacturing are very tight and no oil film is needed, but of course it costs more. We're going to jump right past centrifugal machines as we don't see them very often, and my director is saying I have to hurry up. The second biggest piece of equipment in the compressor room will be the air dryer or air cooler. They're the same thing. People don't realize that when you pressurize air, it gets hot. And so if we go up to 100 pounds per square inch of pressure, the temperature of the air before you cool it will get up to 530 degrees Fahrenheit. Take a look at your oven. It doesn't get any hotter than that with your highest oven setting. So it's very, very hot, and that can cause problems in and of itself. But more importantly, the dew point goes up. The dew point is the temperature at which condensation occurs. In a normal building environment, for example, we live with about a 55-degree dew point. So if we keep temps about that, we don't have to worry about condensation. But for air compressed to 100 pounds per square inch, the dew point rises to 140 degrees Fahrenheit. If you don't get the water out of the air dryer with a dryer or cooler, it's going to come out when the compressed air cools below that. Is it okay? Is it a good thing or a bad thing? Well, it depends. Water in airlines can cause a lot of damage and equipment malfunctions. For example, water in the air used to spray painting will cause the paint to run. And rust can happen on metal parts and all type of pneumatic equipment. However, there's other applications where compressed air, it doesn't matter, such as when you use a sandblaster. That jackhammer being used by the construction crew doesn't care about water in the air. So don't dry air that you don't have to, but you usually have to. So how do you dry? Well, there's two classic ways to do it. The first and most common is you cool it down with a refrigerator type device. They cool the air down to 35 or 40 degrees in order to squeeze out the air and lower the dew point. The compressed air is then warmed back up to room temperature, normally using the heat from the entering compressed air. The refrigerators themselves usually aren't very sophisticated. For example, they won't be attached to a cooling tower, and they'll simply be air cooled. You can improve the performance of these things by lowering the condenser temperature using a cooling tower the way you would with any kind of chiller system. This is something you can think about if there's a lot of energy being spent on drying, but I'd like to point out that we only need to cool the volume of compressed air being used. The CFM is normally not very large. Now, another way to dry compressed air is with a desiccant type dryer. Simply pass the air over stuff that likes water more than air. An example of desiccant material would be the packets you find in electronic equipment or shoeboxes. The problem is that after the desiccant does its job, it gets saturated and it can't do its job anymore. So you have to recharge or dry it after it gets wet. So in industrial settings, the most common design we see is a two-tower desiccant dryer type. And in that case, what we'll do is we'll put compressed air through a dry desiccant, which will capture water until it gets saturated, and then we'll switch over to the other tower. Now we have to figure out how we're going to dry or recharge the wet stuff. A lot of times you're going to take the compressed air you've already spent money on and just fire it through the wet tower to dry it. This is an expensive way to dry, more so than refrigeration. But the key advantage of desiccant dryers is you can get the dew points to 40 degrees below zero. This is perfectly dry, and in cases where you have to have perfectly dry air, this is the best way to do it. If you can, this is a great application for waste heat utilization. If you can recharge the desiccant with waste heat, it becomes cheaper than the refrigeration way of doing it, rather than more expensive. That being said, plants will often do both. Refrigerate all compressed air and then use a desiccant for those applications needing those very low dew points. Well, that's it for the big pieces in the compressor room. Let's move on to filters and separators. If we ignore them, we can lose the performance we've gained by doing a lot of other tricks. First, a couple points about filters. They're going to occur before and after the air compressor, after the dryers, and perhaps after the separators. So there's lots of filters. Most plants will use a service contract with their compressor vendors, which will take care of some of them. But you should realize that the service company's job is to protect the air compressor, and they may not be interested in any downstream equipment. Ignoring them, that is, the filters, can cost you money. The rule of thumb is that for any 1 pound per square inch in pressure drop through dirty filters, we'd see an increase in electricity consumption by 0.5%. Now, for the most part, filters capture dirt or particulates. But the other thing we've got, especially with those rotary screw machines, is oil. Oil is being used as a seal, or at the very least as a lubricant. We need to separate that from both air and water. You will see separators in the compressor room for both oil and air and oil and water. Now, if oil is a problem, and there are already oil separators in place, that's probably the biggest indicator that you're dealing with an oil-flooded screw. For oil in the air, if it's in droplet form, we can swirl the air around and the droplets will fly out. But more often, the oil can be in a very fine mist. So the separator's job is to take the mist and coalesce the tiny little droplets into bigger droplets so that they'll fall out. Water oil separators are usually less important and involve cleaning the water before disposal. When you look at the filters and the separators, you can end up with 5 or more filters. And if your service contract is just for the compressor, you could end up with some surprises. Finally, in the compressor room, you're going to have compressor controls. The role of the compressor controls is to keep the air pressure up and clean air available for the plant. But the compressor operator needs to think about a couple of other things: efficiency and longevity of the hardware, all while dealing with widely varying loads. In most compressor rooms, you'll find 2 or more compressors. The idea is to have a backup. You don't want to shut your plant down and stop making money just because an air compressor has an issue. But since you have 2 or more, how do you operate them the most efficiently? If they're of the same size and age, you can alternate which compressor serves the main load. One week use one, then the next week use the other, and this way they will age evenly and will need maintenance at the same time. Other times you just have an old compressor that's there as the backup, and you operate your newest machine all the time using the old one in an emergency. Ideally, you should not need to be able to meet the maximum load with any single compressor. You can set your compressors up in the lead-lag model. Let's say that I have my one compressor set at 85 pounds of pressure, and I have the second one set at 80 pounds. The backup pressure will not cycle on until the master compressor can't meet the load and has dropped down to 80 pounds. Some systems use 2 or 3 compressors with different sizes, and you can operate them based on matching of the load. So that's an overview of what you'll see in the compressor room, and your job as an energy efficiency expert is to try and improve operations, either by buying something or changing the operational scheme. Let's talk about some supply side opportunities you should take advantage of. Here are the questions we must answer. Are we using the right type of compressor? Is it the right size? How are we operating it in terms of load and unload? What pressure should we operate? Where are we taking in and out the air and the exhaust? What are our filtering practices? And how should we sequence the use of multiple air compressors? And if you were going to buy another air compressor because you're expanding or whatever, which one do you buy and what does it look like? I like to start by looking at the load profile for my compressed air system. Easiest way is to monitor the kilowatt draw from the power panel into the compressors. But this normally requires shutting down the system to hook things up. So when that's not possible, I often look for the load unloaded signature with a stopwatch and counting load and unloaded several times during the day. The question I'm trying to answer is how peak demand compares to the average plant demand. If the compressor is going to be sized to meet the average load, it can't handle the peak load. Now you need to be able to make up the peak load some other way. Let's say that peak load is very short-lived. Then you can use storage tanks. The other way to do it is to run both compressors in order to meet your peak demand. If a single compressor can handle peak load, it's probably running offloaded most of the time, and that makes it a good candidate for one of those variable speed drives. Sometimes you have to tackle end uses, but hey, that is discussed in our next episode. So now we've reached the big one. What pressure do you set your compressor at? There are air pressure consultants out there that tell me that just adjusting pressure settings can make them a handsome living. And that's all they would have to do. You would like to keep your compressed air pressure as low as possible so you're not making 100-pound air when you only need 70. It would make sense that everyone's compressor should be set at about 75, 76 pounds because that's all most pneumatic tools need. But that's not the case. Commonly we see pressures at 100 psi and sometimes as high as 130 psi. When you consider a rule of thumb that you get a 1% increase in energy consumption for every 2 pounds per square inch increase in discharge pressure, you can see where the dollars are going. Let's say you have a problem in your system. You've got pressure drops somewhere, leaks that you shouldn't have. Now the performance goes down, and as a plant manager or the air compressor guy, you have to find a fix, and quickly. So you simply increase the pressure on the compressed air a little bit. And you know what? That makes those problems go away. It just costs you money. And we'll figure out what to do about that later, right? And in reality, you use more than just the high pressure, because as we have higher pressure, we have an increase in leaks and in unregulated use of air. But again, with unregulated compressed air use being sort of blowing applications and tools and air motors and stuff like that, again, we're going to address in some detail in episode 2 of this video series. But the combined effect of raising the pressure and therefore increasing the unregulated use of air is not subtle, and it's why you save so much money by lowering pressure. So what do? You try to get some sensors going so that you know what the pressure is in the system at all times, and you try and look at where the pressure is going when you're at your maximum load. Let's say at your maximum load, your pressure dropped to 80 pounds. So you go out into the plant, you ask everyone, hey, at 2 o'clock yesterday afternoon, did stuff not work because we didn't have enough compressed air pressure? Most of the time everyone says no, everything was fine. And then you know you can turn the pressure of your compressed air system down to 80 pounds and everything will still work. Here's another idea, a common one, based on the idea that it's easier to compress denser air. Cooler air is denser, so you'd like to bring cooler air to the compressor from a cool place. If your plant is air conditioned and you have a small air compressor, during the summer you'd like to use that air conditioned air. However, in wintertime you might well bring that air in from outside. Most people will duct the intake to their air compressor from the outside. I have to say here that this worries some people because of the humidity in summer. Bringing it in from the outside will cause too much water in the air and will create problems for some of these rotary screws. But personally, I've only seen that at my home base, Rutgers University. They duct their exhaust outside but use compressor room air for the intake. Another great idea is to utilize the heat around these air compressors. The engines run hot, and the air as we compress it can be as hot as 500 degrees Fahrenheit. Especially if we have an air-cooled air compressor, and most of the compressors we run into will be air-cooled, you can duct the hot air and just take it through the building. It's clean air, all it did was get heated up, and it will lower your heating bill. Some people worry that it'll cool in the ducts before it gets to where it's needed, but since the heat is otherwise thrown away, any amount helps. Okay, now what do we do about these dryers? Well, the first thing some companies do is to try and dodge having a dryer at all by saying if I've got too wet air, I'm going to let it settle in a storage tank and collect the water from the bottom. Or I'm going to control the moisture by bleeding air into the system as opposed to using a dryer. Time will not permit me to go into the number of reasons why these are bad ideas. And sometimes it's why are you using compressed air in the first place if you could use fans to replace them. But again, another advertisement for our next episode. Just know that in normal cases, you need low dew points of 35 or 40 degrees or less. Now you can operate your refrigerated coolers with a condenser. This is very nice and it can improve the performance considerably. But most people don't pay for that, and at the very least you should make sure that you're cooling your condenser with cool air from somewhere. Again, a good idea to duct the air cooler from the outside in order to cool the condenser side of your air dryer. Also, make sure you're not using your resistive heater to reheat the air that you've now dried. Some old compressors use that because I guess energy was very cheap. So make sure you're using some of that incoming very hot air to reheat that compressed air back up to ambient temperature. Finally, when you're all done with your hardware analysis, you can look and see what kind of control schemes you can use to improve things. Can you run your recips as on-off? Maybe by putting in an extra receiver tank. Can you upgrade to variable speed drives? Or probably, more commonly, when you add an additional compressor, can I make that one have a variable speed drive so that I can match my load to what the system needs? So we're kind of coming to the end of our discussion on the supply side of compressed air. Just want to remind you of a couple things that I think are the takeaways. First, think of compressed air as an expensive utility, the same way you would look at electricity or steam or natural gas. There's a lot you need to do on the supply side in order to achieve what we refer to as best practice, and it helps to know how much all that costs. Secondly, don't count on your service providers or your service contracts to focus on performance. They're interested in equipment maintenance and the lifetime of equipment. They'll come in and lubricate and clean filters to keep everything running, but they will not measure performance or tell you how to improve it. Finally, if you're bored by everything I've said today, and you've seen videos like this maybe 20 times, and you still haven't found the time to do anything in your plant, consider outsourcing more than equipment maintenance. Perhaps consider outsourcing your energy performance to one of these energy service companies. The next video, episode 2, we'll be looking at distribution and end use for compressed air systems. After that, we will tackle industrial cooling. Thank you for watching, and we hope you will send any comments to the link shown here.